Yeah, hello, my name is Pust. I welcome you to the presentation by MUT about novel NDIR sensors for multi-gas sensing. And we just made it in time. And looking at the title that I mentioned, you can ask what is novel about NDIR, and I will come back to that question later. Um, Before I go into the topic, I will explain a little bit about our group of companies which are under the umbrella Nanomic. And to this group of companies belong 13 companies which all work within optics and photonics in different application areas. We have worldwide operations and roughly 600 employees across our group. So in this community, you might actually know a few of our sister companies. Maybe Avantis is the most known for compact spectrometers, light sources, and spectroscopy software. Then we have Sensor-Therm, which manufactures infrared detectors and cameras. We have Spectral Engines that make handheld NIR spectrometers, and also Tech5 might be known quite well for their spectroscopy solutions for process control. And then we have a few other companies which are in quite interesting but niche applications. For example, LambdaTech, who use multi and hyperspectral imaging for phenotyping of plants. We have Art Photonics, which is also known for their specialty fibers from UV to the far infrared spectra. We have recently acquired the Danish company NDIR that uses upconversion technologies to make mid-infrared spectroscopy much more accessible and affordable. So looking at MUT, which is the company that I represent today, we are operating out of Wedel, which is close to Hamburg in Germany. We are more than 100 employees and were founded in 1995 and are actually the core of the Nanomic group. We have three business areas where we operate in different applications. One is industrial sensing, where the gas sensing, which I will talk about today, is located. We also handle fire detection and fire extinguishing equipment there, and also sensors for transportation. Then we have a green tech business area, which is mostly focused on agricultural applications with NIR spectroscopy. And we have a life science business, which makes lab automation for the medical industry. I want to show a few examples what we do for our customers in the green tech field with NIR spectroscopy. So we do not ourselves develop NIR spectrometers, but we use NIR spectrometers, for example, from our sister company Avantis, and bring them into really harsh agricultural applications. As you can difficult to see, but anyhow, as you can see, we put the spectrometer in a box and then mount the box, for example, on a grain harvester so that the farmer can, during harvesting, access already the quality of the grain, like protein and water content and other important parameters, which afterwards are relevant for also for the payment that the farmer receives. A similar box is equipped to manure barrels to online control the amount of phosphate and, for example, nitrate during bringing out the manure, so that the farmer can be sure that he does not overpower the amount of nitrates and phosphates, because that can have as a consequence that the field might be shut down. And as you can imagine, for NIR spectroscopy, it's a quite challenging environment with vibrations, shocks, high temperatures during harvest, and also the farmer is not very sensitive about cleaning his equipment, so it must also withstand being cleaned with a high pressure cleaner. What I show here is a different application of NIR spectroscopy. It's an handheld instrument which is not based on a dispersive NIR spectrometer, but it integrates in a very compact form factor a Fabry-Perot interferometer, where you can, with a movable mirror, tune the wavelength that is transmitted and then make a continuous wavelength scan in the near-infrared range. So it's very compact, very robust, and uses software models that are uploaded to the cloud that can match specific applications. For example, like you see here in a box for the police enforcement to check for drugs if they make a traffic control, for example. Or since recently, at least in Germany, you can use it to control your THC content of your green plants that you are allowed now to keep 3 pieces of at your balcony. Could also be equipped with models for textile identification to differentiate between different kinds of natural or artificial textiles. Now, really, I want to introduce to you the application of NDIR, so non-dispersive infrared spectroscopy, to you. And yeah, as initially said, NDIR as such is not a new technology, but I think it's quite novel how we use the technology, modify it, and implement it for demanding applications. So this is not a simple single gas or dual gas sensor. It's an advanced multipath wide optical cell, so we can achieve a very high or long absorption length and thus high sensitivity in a very compact form factor. So the total volume of that box that you see over there is roughly 2 liters, so it's a box like of that size. And because of that long absorption length, it can measure from single-digit ppm levels up to several thousand ppm, or for some gases also up to many percent. Inside the detector, we have a proprietary 9-channel detector that we had designed and manufactured for our application. One of these 9 channels we use as a reference channel, so we can measure up to 8 gases simultaneously with one single box. And the channels can be customized to the customer's application, so we can specify and mount different bandpass filters in front of the sensor elements to focus on the specific absorption bands of the gases that the customer's application require. As an optical technique, there are no chemical reactions in the sensor. You also do not need any on-site test gases because the sensor comes pre-calibrated individually from our factory. There are no moving parts, so it's quite robust. And also for industrial monitoring applications, very important, it's long-term stable. So we do not make a business out of asking you to send back the unit once a year for recalibration, so that's not necessary. And because we measure up to 8 gases simultaneously, we are also able to make a cross-compensation so that you do not have interference from other gases that you have in your gas matrix. I will show that a little bit later. And as you can see, we have filters, for example, for a lot of hydrocarbons, for water vapor. But that is just an example and can be tailored to your application. Here you get a little bit of idea how that looks like internally. So down here we have the gas volume, which is roughly 300 milliliter. There we have the broadband infrared emitter as the heat source. We have the mirrors for the white cell and the 9-channel detector. And what I want to show here is that we also have designed the modules so in such a way that also other detector types like electrochemical detectors, metal oxide detectors, or semiconductor sensors could be integrated for gases that you cannot measure with infrared absorption technology. And of course, as with every gas measurement, we also need to consider temperature, pressure, and humidity to compensate these cross sensitivities. We measure this, of course, internally, but we also measure these parameters externally to control the unit. Interfaces are pretty standard, but could also be different data communication. Right now, we have implemented a serial communication. So the unit doesn't output any voltages or currents. All the processing takes place on the unit. There's a firmware and a processor on the unit that takes the raw signals and turns them into physical calibrated concentration values that are output as a data stream. Of course, you know, I assume how NDIR works. Nevertheless, I show the principle here again and show the difference between a classical near NDIR detector that you can see on the show here and on several booths, where you simply have an emitter, a tube for the absorption length, and then one or several detectors. And depending on how sensitive you want to become, this absorption length might be 20 centimeter, it might be half a meter, and if you want to be very sensitive, it might be even 1 meter. But if you have that straight approach, really your equipment becomes quite bulky. And to avoid that, we use that wide optical cell where we have multiple reflections between several mirrors to achieve a very compact design. Here I show an example of the exact configuration of the gases that I've shown previously. You see the gases listed here, and of course it would be nice if every gas had its own sharp individual absorption band, but unfortunately, but that it makes it also interesting, it isn't the case. So if you have several gases, you see that the absorption bands overlap. They can be very different in magnitude, so it's a logarithmic scale, so there are really magnitudes of difference in the absorption strength. And if you have such a complex gas matrix, you really need to take a lot of care to get the real concentration data out of this measured spectral information. And that is what we do. One thing, of course, is the hardware that we have designed and manufactured. And equally important is the software that takes care of this, let's say, data mess. So we, in principle, with such a processing algorithm, you can take in any kind of data. NDIR could be NDUV, could also be photoacoustic spectroscopy data from different sensor channels. And then you, of course, need to do a multivariate calibration before you really do a measurement. We do that for every single unit in our climate chamber with the gases that the sensor is designed for. We have a large matrix of gas concentrations, first individually, then combined pressure, temperature variations. So such a calibration can take up to 1 week for a quite large space of parameters. And then that calibration is stored on the unit, and when the raw data come in, multivariate algorithms use that calibration and turn then, considering also the physical parameters of pressure, temperature, and humidity into calibrated output values that are handed over to the user. I want to show you one example where that is very advantageous to conventional approaches using a multi-gas sensor. What you see here is a power transformer that is used for distributing the electrical energy that we use every day. And these large power transformers are cooled with insulation, insulated with oil and also cooled with that oil. And because that oil has to tackle a lot of electrical power, it will degrade over time. There are certain processes going on, certain small failures, so that the long chains of the hydrocarbons break down into smaller components. And this liberates gases into the oil that are dissolved in the oil. And when you're an expert of DGA, dissolved gas analysis, the concentration levels and the combination of gases, the rate of the generation of these gases tells you a lot of what is going on in your power transformer. It also tells you when it is time to exchange the oil. And of course, you want to do that as soon as necessary to avoid a power failure, a breakdown of the energy supply. But you also do not want to do that too often, because you can imagine there's a lot of oil inside there, which is a cost factor. And what these operators do traditionally is that they go to the transformer, take an oil sample, send that oil sample to a laboratory, get it analyzed, and then get the result, which can take a few days. So it takes time, it takes manpower, and sometimes it might be too late, or you decide to change the oil too often just to be on the safe side. So the next step would be that you have a mobile unit, which is shown here. You have a suitcase with a mobile laboratory, but again, it's a little bit faster, but you still have to go to the power transformer, and you can only check infrequently the condition of the power transformer. And now our mobile, our online measuring gas sensor is fixed directly to the power transformer. They have an apparatus that extracts the gas from the oil, feeds it into the multi-gas sensor, and in this way they can 24/7 online monitor exactly the condition of the power transformer, which of course is a huge advantage compared to the traditional approaches. Okay, and now to something completely different, which is brand new, so it didn't make it into the announcement on the webpage. I want to introduce to you our brand new photoacoustic spectroscopy sensor, which you can see here. Yeah, from this side, a little bit more interesting. So photoacoustic spectroscopy, again, is not a new technology, but now is the time to really make use of it. And because in the recent past we have received several requests for ozone measurements for different applications, we saw that there's a need for an ozone sensor that can measure very low concentrations, like ppb levels, and very high concentration on the percentage level simultaneously. Not simultaneously, but with the same detector module. Because the low values are important for clearance measurements. So if you use ozone for disinfection, for example, or for treatment of archaeological artifacts, you need to open your equipment again, and then you want to be sure that the operator who approaches it is not put into a hazardous situation by ozone. So you need to be sure it's above a certain, below a certain ppb level. And for the process control, you want to measure these high concentrations. And traditionally, the operators, they need two different devices to have these two challenges solved. And here it is really quite nice and handy that photoacoustic spectroscopy, compared to other technologies on the market, has an extremely high dynamic range, which allows to measure these broad range of concentrations with just one module. It also has the advantage compared to other technologies, also compared to NDIR technology, that it doesn't have any zero drift. If you look at NDIR technology, you have very high signal at zero concentration gas, and then it goes down. So you always have a zero level that you need to calibrate. Here it's the other way around, like you know it from traditional detectors. When there's no gas, there's no signal. So it has a stable 0 point, which is quite nice for operations where you can't or don't want to calibrate your sensor once in a while. Another nice thing is that it's quite easy to adapt the sensor to other gases. It's a matter of the right wavelength for the excitation. And how that works is actually quite easy. You have a small gas chamber where the gas flows through, and the sensor is designed in such a way that you get an acoustic resonance when you excite the gas with pulsed radiation. So the pulsed radiation is absorbed by the gas at the right wavelength, which is turned into heat when it's released, and that heat turns again into a pressure change, which can be detected as sound with a microphone. And there it's quite lucky that the development of mobile phone microphones has taken leaps in the last years. So they are very cheap products and they are very sensitive. So you can actually detect these pressure and sound changes with very cost-effective equipment, which also makes the new PIS implementation very attractive for gas measurement. Okay, so I think that was what I wanted to present. We have time now for further questions. And of course, you can visit us at our booth here in this hall, 251, a little bit diagonally across the hall, where we also show our other equipment and where you can discuss your application with our experts. Thank you very much. Don't be shy. Okay, have a nice lunch. Thank you.